Throughout history, water has been a common thread in the rise and fall of various civilizations. Irrigated agriculture was the cornerstone of the first civilizations in the arid areas of the North American continent. When the first European immigrants arrived in the southwestern United States in the 16th century, irrigation was already established as a necessary part of agriculture. Just as the management or mismanagement of irrigation water has caused the rise and fall of earlier civilizations, it also affected the success or failure of many early homesteading efforts in the United States. While advances in science and technology have improved irrigation methods, the need to increase the management of irrigation water has become increasingly important to today's agricultural producer. Higher energy and labor costs, declining groundwater levels, competing demands for water, and the importance of maintaining water quality now require agricultural water users to seek new ways to manage irrigation water supplies. To survive in today's economic climate and cope with increasing environmental constraints, producers are looking for ways to improve their level of irrigation water management. Regardless of the type of irrigation system used to apply water, the producer must make two important irrigation decisions. 1. When should I start the next irrigation? 2. How long should I allow the water to run? Experience has shown that the answer to these two important questions lies in the use of soil moisture measurements. Monitoring the soil moisture gives the producer an open window into the root zone of the crop and reflects the combined effects of climate, crop growth stages, and the existing irrigation system. The simplest and oldest method of measuring soil moisture is by the evaluation of the soil's appearance or feel. By the use of a hand auger, soil samples are taken by the producer throughout the soil profile. The appearance of the soil is then compared with established guidelines to estimate the amount of soil moisture available to the crop. Although self-help brochures are available from your local Soil Conservation Service office explaining this method, many producers now prefer to use soil moisture sensing devices instead of soil borings to monitor soil moisture changes. Soil moisture sensing devices are placed in the irrigated field at locations which reflect the greatest moisture stress on the crop. With basin, border, or furrow irrigation, this location is usually 2/3 to 3/4 of the way down the irrigation run. With sprinkler irrigation, the location for the soil moisture sensor should be approximately 3/4 of the way down the lateral line and at locations of noticeable plant stress. When irrigating orchards, the soil moisture sensing device should be placed approximately 1/2 to 3/4 of the canopy distance from the tree trunk. Regardless of the type of irrigation system used, the soil moisture sensor should always be placed at a location that is representative of the crop stress in the field, and also at a location that is easily accessible to the producer. Two soil moisture sensing devices that are gaining popularity among producers are resistance blocks and tensiometers. The tensiometer is a hollow plastic tube filled with distilled water, fitted with a porous ceramic tip at the lower end and a vacuum gauge on the upper end. A colored additive is added to the distilled water to retard bacterial growth and assist in visual observations of the tensiometer's water level. This instrument is placed in a small hole drilled or punched in the soil to measure the tension or suction exerted on the soil by the crop. Care must be taken to insert the tensiometer in an area of crop growth that is representative of the field to be sampled. The suction created by the soil on the tensiometer's porous tip is converted to a visible meter reading on the tensiometer. The higher the gauge reading, the drier the soil. Tensiometers are read at regular intervals, preferably at the same time of the day, to reflect the true water use of the growing crop. Readings are plotted in a logbook for easy analysis by the producer. Tensiometers are available in various lengths to accommodate a wide range of root depths and measurement intervals. The 12, 24, and 36-inch lengths are the most frequently used. A group or cluster of tensiometers is usually placed in the crop root zone, and the gauge readings are recorded regularly. By monitoring the changes in soil moisture before and after an irrigation, the producer can accurately predict at which tensiometer gauge reading irrigation should be started and reflect the penetration depth of irrigation water and rainfall in the soil profile. Because of the limited range of soil tension that the tensiometer can measure, the tensiometer is more suited to situations where frequent light irrigations are applied, such as with shallow-rooted crops or sandy soils. Resistance blocks, on the other hand, can be used over a much wider range of soil moisture levels and are especially useful in irrigated areas where large soil moisture deficits need to be monitored. While the tensiometer measures the tension or suction in the soil profile, the resistance block method uses the soil's ability to conduct an electrical current to monitor soil moisture changes. Stainless steel screens or electrodes are embedded in a stabilized sand or gypsum material, which forms the basis for the resistance block. Prior to placement in the soil, the resistance block is soaked in water to accelerate the initial block reading. A small hole is drilled or punched in the soil profile for the resistance block. Care should be taken to surround the newly placed resistance block with saturated soil that is representative of the block's location in the soil profile. Wires connect the blocks to the soil surface, where a portable metering device is connected to the buried blocks. A handheld meter induces an electrical current across the buried sensing blocks and measures the block's resistance to the electrical current. These wires are then depth-coded and the location marked so that they can be easily found later by the producer. The wetter the soil, the lesser the resistance to the electrical flow, and the lesser the tension that the plant has to exert to extract the soil moisture. This resistance is converted to an easily readable indication on the portable meter. Like the tensiometer, the resistance blocks are usually placed at 12, 24, and 36-inch depths in the soil profile. Meter readings are plotted before and after each irrigation, giving a clear picture of the existing soil moisture content in the crop root zone. Both tensiometers and resistance blocks are relatively inexpensive and are available from numerous distributors. Use of these devices can take much of the guesswork out of irrigation water management and can give producers the opportunity to reduce the amount of water applied, thus reducing water costs, percolation, and nutrient losses, and increasing crop yields and economic returns. More detailed information on the use and operation of soil moisture monitoring devices and the techniques described in this video can be obtained from the local office of the Soil Conservation Service.